Okay, problem 45 has things in it. Conservation of energy that we're going to use for balls. You can again get this guy will bounce back, it will go forward, but we also need the numbers. And C is to find the maximum height to which these balls will bounce back. Okay, the first part, I expect you to know how to do it now, and you probably all can. Figure out energy, we have in mechanical, which is potential plus. In the end, it's just kinetic. So you should be able to whip up this formula and then rearrange it. And so your initial velocity of the ball before it bounces, before it acts the heavier stationary ball, is 5.56 meters per second. From now, here's our data, and I'm going to use my 556 as initial velocity. So we are considering right before they collide. That's the velocity of the ball. So that is our initial momentum. So initial momentum of the first ball is 1.50 times 5.6. The second ball is stationary, so therefore 0. And these two are question marks. We don't know either of these. Since we have one equation with two variables, we need to bring up the second equation for conservation of kinetic energy. Then, if you have looked at a previous problem that is like this, you hopefully remember that what we did here, we got rid of 2. The second, what I'm doing is I'm rearranging. I'm taking out M1, dividing it here, so I get M1, and these guys cancel. And then since I'm interested in either this or that, I'm going to pick this one, and I'm going to rearrange this formula in order to get my V1 final squared. So I will have to take this right here, put it with a minus on the other side, and then divide. Well, not divide, it's already given. Then I'm going to go back. So right now I have, that is a variable, that is a number, and that is a variable. So in order to solve this equation, I need to substitute V2 final through V1 final, and I'm going back to that equation over here. I ditched the 0, rearrange, and get my V2 final. Again, the way we do it, we see M1 and M1 here, so put M1 in front of the bracket, which gives us a V1 initial minus V1 final, and divide all that by M2, and I'm just putting this in front of the bracket. So now I'm going to take this whole thing and put it in this formula and square it. So there we go. That is our big mama. So now, oops, it's not 38, sorry. Anyway, so we continue on, and again, do not go ahead and square this because it's just going to give you too much trouble. So what you need to see here is if you put this one on this side, that will be the difference of squares, which will be the difference multiplied by the sum. So we do this one, and I also take this from under this square. So this is squared and that is squared. That way I can get rid of this and this, and square will go away. So instead of the difference of squares, I'm basically rewriting this into this product. Then that, you already see how that's done. And then since I have that and that, I can cancel the square here. And then all I have left is, that's it, right here. And then I just open the brackets and end up with just VI, V1I minus V1F. And then basically these are, that's a number, that is my variable. And that variable has a factor here and has a factor of 1. So what I'm going to do, I'm going to rearrange. I'm going to multiply everything by M2 so I don't have any fractions. So multiply by M2 both sides, so that's where this M2 is coming from. Then you rearrange everything with V1 initial on one side with V1 final on the other side. We're looking, that's a number, we're looking for this one, so rearrange this and end up with that formula. So plugging in the numbers that we have, that gives us a negative 283 meters per second, which makes sense because it's a lighter ball, so it will bounce backwards. If you take the previous formula which we had from the conservation of momentum and plug the numbers in the way we have it, you will have 274 meters per second. That is not quite the right answer. And I'm going to show you how to get, let's say, what if they ask you for the velocity of this ball? And you would need to figure it out without finding that velocity. The way you do it, so you have this, that came from the conservation of momentum. This we already have. So what I do is I take this right here and put it instead of that. To make sense, right? So V1I minus this contraction right here. Then I'm looking inside this formula. It has the denominator. So in order, that's the same variable right here. So in order to subtract the fraction from a whole number, I need to put them to the same denominator. So I just multiply V1 initial by M1. Well, what you see is here. This is basically 1. And then, since it's the same factor, you can see that M1 subtracts from M1. And then this guy, that's a minus, and that's a minus, so that becomes a plus. So that's how you end up with 2M2. And then M1 plus M2, you open the bracket, this goes away. So this should be, this should be 2M1, sorry about that. And then the sum of those two masses times V initial. Again, that's M1. Little fault. All right, so then you just plug in the numbers and you actually get the right number, which is 273. To answer C, again, that's back to the beginning. Now we have kinetic energy turning into potential. You just write the plug in the numbers for each of the balls. So you do 283 over 19.6, and then 273 squared over 19.6 gives you that. And that's it.